going to look at polynomial and rational functions. If you'll recall from the last lessons, we talked about linear and quadratic functions and their graphs. Both of these functions are special types of polynomial functions. A polynomial function is in the form f of x equals a with a subscript n, so we would just say a sub n times x to the n plus a sub n minus 1 to the x times x to the n minus 1 plus, and then of course we would work our way all the way down if it's in descending order to our linear term, which is a1x, plus our constant term, which is just a0. an, which is the first term there when it's in descending order or standard form, that's known as our lead coefficient. And all of the a's are your coefficients, so they're the numbers attached to the variables. And then we have n, which is our power or degree. And when it's written in standard form, the n is the degree of that polynomial. A power function is a specific type of polynomial function. It's actually the simplest polynomial function of higher degree. And it's in the form of f of x equals x to the n. So x squared is a power function. X to the third is a power function. Basically, the polynomial functions will mimic the power functions. And another important feature is that the graphs are always smooth curves. So in other words, there won't be any breaks in the graph, any jumps, any gaps. Okay, let's take a look at this polynomial function and let's graph it. So one thing we can do is we can use transformations to graph, right? So if I take a look at this polynomial function, I see that my degree is 3. So that means that my parent function, my most basic function, is f of x equals x cubed. So let's make a table and let's plot our parent function. Okay, I'm going to plug in some values into x cubed. So negative 2 to the third is negative 8. Negative 1 to the third is negative 1. 0 to the third, 1 to the third, 2 to the third. And now looking at this, as you know your transformations, the negative is going to reflect the figure over the x-axis. And to do that, we're going to multiply our y values by negative 1. And then the other thing that's going to affect the y's will be the plus 3. Remember, that's a vertical shift, and it's going to go up 3. So we're then going to add 3 to each of the y values. And then the minus 2 is a horizontal shift, and it's going to go to the right 2. Because my h value is really a positive 2. So that means I'm going to add 2 to all of the x values. So when I do that, let's add the 2 to the x's first. Negative 2 plus 2 gives us 0. Negative 1 plus 2 is 1. 0 plus 2, 1 plus 2, and 2 plus 2. So there's my x coordinates. For my y, I'm going to multiply by negative 1 and then add the 3. So negative 8 times negative 1 is 8, plus 3 gives me 11. Negative 1 times negative 1 is 1 plus 3, which gives me 4, and so on. Now I'm going to plot these points. So 0, 11 would kind of be like right about there. 1, 4 would go here. 2, 3 is going to go here. 3, 2. And then 4, negative 5. And the shape of a cubic function, an x to the third, kind of looks like this. So we know that it really just took x to the third and it reflected it over the x-axis, and then it shifted it to the right 2 and up 3. Okay, here's another example. And for this one, we're going to use a graphing calculator to graph this and kind of look at what we notice. Okay, and I'm going to use Desmos to graph this. You can use your graphing calculators. So it's 8x to the third minus 12x squared plus 2x plus 1. Okay. Now, what is something that we notice about this? As x gets really large, right, as we move from the origin to positive infinity in the direction of x, so to the right, the graph is going upwards. And as x is getting smaller, as you go to the left, the graph is going to be pointing downwards. Okay, so that's something that I notice. The other thing I notice is that there's 2 turning points. There's a turning point right there, so the graph is switching direction. It's an inflection point. And then there's another turning point right there. So it's got 2 turning points, okay? Now, let's see if I can, I don't think I can take this image and paste it, but I am going to show you that, so if you're using your graphing calculator, if you hit second table, after you type in this function into y equals, you're going to find a table and it will give you some values that are on the graph. Like for instance, I know from my graphing calculator that the point negative 0.2 comma 0 is on the graph. As you can see, that green point just popped up. And I also know from looking at the table that 0.09 comma 1.1 is also on the graph. And let's do one more, like 1.2 comma 0 is on the graph. That's my x-intercept that just popped up. Okay, so I would get about, as many points as you can, 5 or 6 points, and then graph it. So the points, again, that you found on the table in your graphing calculator are as follows. Okay, so negative 0.20 is going to be right about here maybe, and then 0.09 and 1.1. Let's see, so 0.09 and then 1.1, it's going to go maybe right about there. And actually on the other side, because it's positive, so it's going to go like maybe right about there. And then we've got 0.5 and 0, and then 0.9 and negative 1.1. And then we have 1.20. Okay, and as we saw earlier, right, as x was getting smaller, the graph was pointing down. And as x gets larger, the graph is going to point up. So it kind of connects together and looks like this. And we can also see those 2 turning points that I talked about. One of those turning points is right there. The other is right there. And we're going to talk more about them when we get into calculus. Okay, but we can write down here. So as x increases, y also increases. And as x gets smaller, y gets smaller. And we also note that there's 2 turning points. Okay, so some things we notice. If you'll also notice here, the domain is all real numbers. You can plug any number in for x and always get a different y. And then the range is also negative infinity to positive infinity because the graph goes on forever in both up and down directions. For the next one, you can try this one on your own. And then if you would like to get a better picture of it, you're going to want to go into the window and change the window. So you're going to want to change the x window from -3 to 5. So like that's going to be your x min, and that's going to be your x max. And then you would want to change your y min in your window to -50 and your y max to 50. And then you'll get a better picture of the graph. Okay, so try that on your own, see how you do. Here's some properties for polynomial functions, so you can also pause the video and read through it. A polynomial function of degree n can have at most n minus 1 turning points. So what that means is if the degree is 3, as we saw in the example I did, right, it'll have 3 minus 1 turning points at most. So 3 minus 1 is 2, and we saw that it had 2 turning points. Now, that doesn't mean it'll have 2. It could have 1 turning point, but it can't have more than 2. Conversely, if the graph of a polynomial function has n turning points, it must have degree at least n plus 1. So if it's got 2 turning points, the lowest degree it possibly could be is 2 plus 1 or 3. But it could also be degree 4 or degree 5 or so on. Because remember, the rule just stipulates that degree n has at most n minus 1 turning points. If the graph of the polynomial function of even degree, both ends will go up or both ends will go down. And when the polynomial function is an odd degree, one end goes up and the other end goes down. So one way to think about that is, and one way to determine that is to look at two things. You're going to look at the lead coefficient and the degree. Those two things will determine whether the graph opens up or down. And we call that end behavior, all right? So when you have your lead coefficient is, let's say, positive and the degree is odd, the graph is going to go in opposite directions. One side's going to go up, the other side's going to go down. If it's negative and odd, again, it's going to go in opposite directions, but this time the left side goes up and the right side's going to go down. If it's positive and an even degree, so like x to the 4th, both ends are going to point up. And if it's negative and even, like negative x squared, we know from talking about quadratics that would be concave down. Both sides are going to point down. And then the last property is if the graph goes up as x becomes a large positive number, the lead coefficient must be positive, as we saw in the example I did with the x cubed. If the graph does go down as x becomes a larger positive number, the lead coefficient is negative. Here's another example where you've got two polynomial functions and there's no numbers there. And what you want to do is identify any possible degree of the polynomial in each figure and give the sign, is it plus or minus, for the lead coefficient. Next, let's talk about rational functions. So rational functions are in the form of f of x equals p of x divided by q of x, okay, where p of x and q of x are polynomials. Okay, and q of x cannot equal 0 because then the function would be either undefined or you would end up with, you could end up with 0 divided by 0, which is indeterminate. So a rational function is just a fraction, but in the numerator and denominator are polynomials. Let's graph the most basic rational function, which is a parent function. It's y equals 1 over x. And all I'm going to do is plug in these values for x. So what I would do is go to your calculator. You're going to type this into y equals, and then go to the table, okay, and substitute or look for these values. Now you might have to change the table. I believe it says delta table to count by 0.5 to get some of those values, but you can also just plug in these values quite simply. So, you know, if it's easier for you, you can, let me just erase this, you can just do 1 divided by negative 0.5, and then you could do 1 divided by negative 0.2, and then 1 divided by negative 0.1. So if it's easier for you to do that, that's fine. But you're just going to fill in those numbers, and let's get some y values. So when you do that, you should get the following. And if you take a look at this table, right here in the center, two things are happening, okay? So first of all, if you look at the x's, as you're going this way and this way towards that arrow in both directions, x is approaching 0, right? So as you move this way and as you move that way, x is approaching 0. Okay, and then also what's happening as you move this way and as you move that way, the absolute value of y is getting larger. Okay, so you can see here that the numbers are getting bigger and bigger, the absolute value of those numbers as x is approaching 0. So if we were to summarize that, we could say something like, as x gets closer to 0, the absolute value of y is getting larger. And something else that we notice is, as the absolute value of x gets larger, right? So if we were to go this way or this way, so in the opposite direction, then that means that y is going to get closer to 0. Those numbers are going to go closer to 0. So if I start here and go to the right, and start here and go to the right, or sorry, start here and go left, start here and go right, the opposite direction the arrows are pointing, you can see that the y's are going to approach 0. So it kind of switches roles, right? So you could also say, something else you notice is that as x, the absolute value of x, gets larger, then y equals 1 over x gets closer to 0. Now, how would I graph something like this? Well, if we think about the domain refers to x. If I was to substitute a 0 in for x, 1 divided by 0 is undefined. So that means that 0 is not a good number. Okay, we have to remove it from the domain of this function. So that tells me that the domain is going to be all real numbers except 0. So from negative infinity to 0, and then union 0 to infinity. So 0 is a bad number, right? When x equals 0, we're talking about the y-axis, right? That's another name for the x equals 0. So right there, that's going to be what's called a vertical asymptote, okay? And a vertical asymptote is just if a function gets larger and larger in magnitude without bound, so as it keeps going on and on and on, as x approaches the number, we'll call that number k, then the line x equal k is a vertical asymptote. And think of an asymptote as just a line that a graph gets really close to but doesn't intersect. So the graph's going to get really close to that dashed line, but it's not going to intersect it. And to show you, I can plug in some values here for x, right? Actually, I have values in the table. Why don't we just use those? So if I was to graph -1/2 and -2, it's going to be like right about there. -0.2 and -5. So you can see it's getting closer to the y-axis. -0.1 and -10. Okay. And it's going to get close and close and close. But it's actually not going to go above the x-axis. The x-axis is going to be what's called a horizontal asymptote. And we call that y = 0. So a horizontal asymptote says if the values of y approach a number k as the absolute value of x gets larger and larger, then the line y = k is a horizontal asymptote. So again, an asymptote is just a line that a graph approaches but doesn't necessarily pass through. And here we're talking about this horizontal line that the graph's getting really, really close to but is not passing through. Okay, and I know that because we already said that as the absolute value of x gets larger and larger, right, the function itself gets closer to 0. So as x is going to get larger, right, as I go this way, the graph's going to get closer and closer to 0. It's never going to actually equal 0. And you'll see that when we graph the other branch of that figure. So if I was to graph like 0.1 and 10, so 0.1, 10, it's going to be up there, and then it would be 0.2 and 5. So like right about there, and then it was 0.5 and 2. And then look at your other numbers. You got 0.01 and 100. And, you know, if you were to keep going, like plug in, you know, x equals 1 and x equals 2 and so on. So if you plug in x equals 1, you'll get 1. If you plug in x equals 2, you get a half. Plug in x equals 3, you get a third. Plug in x equals 4, you get 1/4. What's happening? The fractions are getting smaller and smaller and smaller. They're approaching 0, but they're not actually ever going to equal 0. Okay, you can't, in other words, find a value for x that when you plug it into that function, 1/x, it's going to ever y would ever equal 0, right? Think about it. So it's going to get really close to the x-axis, but it's never going to go through it. So that's what the graph looks like. And as you can see, the range is the same as the domain. Again, y will never equal 0. So the range is all real numbers except 0, just like the domain. Now in this next problem, we have a rational function, but it's slightly different, okay? How do I know it's a rational function? Well, again, it's a polynomial divided by a polynomial. Now, what happens is I need to find the if there's any vertical asymptotes. And as you saw in the last example, to do that, we're going to set the denominator equal to 0. So if I set the denominator equal to 0, I get it x equals -1. Okay? So I'm going to remove that from the domain. So my domain is going to be -infinity to -1, and then -1 to infinity. So the parentheses, remember, signify that -1 is like a boundary, but we're not including it. It's an open interval. Now here's the deal. If I was to plug in -1 in the denominator, I would get a 0, right? But if I plug in -1 in the numerator, I also get 0. So essentially what I have is 0 divided by 0, okay? Now, if I take that numerator and I factor it. So if I factor x squared plus 3x plus 2, I get x plus 2 times x plus 1. And then I put the denominator x plus 1. If you notice, the part that gave us the bad number, -1, it's going to cancel out. So it was removed. We call that a removable discontinuity. All that's left is x plus 2. So now there's no longer a vertical asymptote at x equals -1. There would be if we didn't remove it, but we removed it. That means that there's going to be a hole left behind, okay? So there's a hole at x equals -1. Now if I want to find that y value, I'm just going to plug it into my leftover function. So if I plug in -1 for x, I get -1 plus 2, which is 1. So that tells me there's a hole at -1, 1. Okay, so I'm going to put an open circle there. That's going to represent the hole. And then all I need to do is just graph y equals x plus 2. So if you'll recall, to do that, you're going to put a dot on 2. So begin at 2. And then you're going to rise 1 and run 1 because your slope is 1 over 1. So really your graph is just going to look like a line because that's what x plus 2 is, right? We learned that already. Okay, you can pause the video and now try the next problem on your own, and then we're going to look at average cost. Okay, so what is average cost? It basically says if the cost function has the form c of x equals mx plus b, which we learned that m is the marginal cost per item, b, remember, is your fixed cost, and I should tell you what x is as well. X is just the number of items produced. Then the average cost per item is given by the following function. So anytime we deal with averages, we put a bar over it, so that we would just call that c bar of x is equal to the cost function divided by the number of items produced, right? That's going to give us an average. If you think about an average, how do we find an average? We add a standard average, we add up the value, and then we divide by the number of numbers, right? So we're just taking the cost function and dividing the cost by the total number of items produced, or by each item produced. And we end up with, if we replace c of x, it's mx plus b, and then divided by x. So suppose the average cost per unit, c bar of x, in dollars to produce x units of yogurt is given by c bar of x equals 600 divided by x plus 20. So if I want to find c bar of 10, that's telling me that there's 10 units of yogurt, and I'm trying to find the average cost of selling 10 units of yogurt. So to do that, I'm going to have 600 divided by 10 plus 20, which is just 600 divided by 30, which ends up being $20. So that just tells me the average cost for every 10 units of yogurt sold is $20. The next thing we need to do is give the equations of any asymptotes on negative infinity to infinity, so all real numbers, and find any intercepts. Well, we know from just a few minutes ago that to find the vertical asymptote, we're going to take the denominator and set it equal to 0. So if I set x plus 20 equal to 0, I get x equals -20. So that's where there's a vertical asymptote. Now, for horizontal asymptotes, there's actually kind of a rule, which I'm going to give to you. And if we have room for it, we can squeeze it in the notes here. We don't have too much room for it. So let me put it down here with the problem. Okay, so when you want to find a horizontal asymptote, there's actually three scenarios. Let's say you have this function here, and let's say it's ax to the n over bx to the m. What you're going to do is you're going to compare the powers, the degrees, the n and the m. If n is greater than m, there's no horizontal asymptote. Okay, now there could be a slant asymptote. We also call them oblique asymptotes. And the way you determine that is if the power up top is greater than the power on the bottom by 1. So if you just take the powers and subtract them and get 1, that means there's an oblique asymptote, which you would have to find using long division. Okay, if n equals m, so if the degrees are the same, the horizontal asymptote is just going to be y equals a over b. So you just simply take the coefficients and divide them, and that's your horizontal asymptote. Now for this, the other option is n could be less than m, so the degree up top could be smaller than the degree on the bottom. If that's the case, it's really easy. It means that the horizontal asymptote is y equals 0, which is just another name for the x-axis, right? So here, if we look, right, 600, there doesn't appear to be a degree up there, but there really is. You can attach 600 to x to the 0, because anything to the 0 power is 1. So that tells me that n is 0, and my degree down here is m, which is 1. So since the degree up top is smaller than the degree on the bottom, that tells me that my horizontal asymptote is the x-axis. So for this problem, the horizontal asymptote is y equals 0. And then to find any intercepts, if I want to find the, so first of all, there's never going to be an x-intercept, right? Because to find an x-intercept, we would set y equal to 0 there. If I want to find the y-intercept, though, I'm going to just replace x with 0. So to find the y-intercept, I'm just going to find f of 0, basically. Well, in this case, it would be c of 0, right? So I would just plug in 0 where there's an x, and you get 600 divided by 20, which is 30. So the y-intercept is going to be 30. Okay, and again, there's no x-intercept because the x-axis is the horizontal asymptote, so the graph's never going to intersect the x-axis. And that's it for that video. If you have any questions, please feel free to reach out. Have a great day, everyone.